Hello friends, this is Jim with Science Talk. In this video I want to discuss with you isotopic fractionation. Before I do so, please allow myself to remind you to subscribe to my channel, and please share my videos with others. I can be found on YouTube, I can be found on Steemit, I can be found on Tumblr, as well as Google. I hope you will consider becoming a patron and supporting the work I do by subscribing to my Patreon page, patreon.com/Science Talk with Jim Massa. If you are a patron already, I thank you for your support and continued support. So, isotopic fractionation. What is that? Basically, it allows us to look at the ratios of different isotopes of an element. This is very, very important because this is how climate scientists, this is what they do to reconstruct past climates. And the information is extremely important, extremely helpful, extremely informative. And the technique is pretty solid. In fact, it's extremely solid. So you may recall that an isotope is basically the different number of neutrons found within the nucleus of an atom. Most of the mass of an atom is found in the nucleus, where it's made up of protons and neutrons. Now, the number of protons defines the element. If I have an atom and it has 6 protons in it, it is a carbon atom. Change the number of protons, you have a different element. If it is 7 protons, that is nitrogen. 8 protons, that is oxygen. Right? However, and protons of course carry a positive charge, and usually whatever number of protons you have, there's an equal number of electrons, so that you have a neutrally charged atom. Not going to get into the chemical bonding where you create ions and all that kind of stuff. You know, don't want to turn this into a chemistry course yet. But if you change the number of neutrons, then you change the isotope. Isotopes are basically different forms of an element. So, let's take carbon. Carbon has 6 protons. It typically has 6 neutrons in the nucleus. There are some forms of carbon where there are 7 neutrons found, and others where there are 8 neutrons found. So now, if you want to add up the mass, typically define the mass of an atom, you add up the number of protons and neutrons. So when you hear carbon 12, that's because you have 6 protons, 6 neutrons. 6 plus 6 equals 12, last time I checked. But then you have carbon 13, 6 protons, 7 neutrons. Carbon 14, we're familiar with carbon 14, 6 protons, 8 neutrons. We can do the same thing with nitrogen. Nitrogen has 7 protons. Nitrogen 14, 14 minus 7 means there's 7 neutrons. But there's also nitrogen 15. 7 protons, 8 neutrons. Oxygen. Oxygen will come in various isotopes, typically O16, O17, not as often, and O18. O16 and O18 are very, very common. So oxygen is atomic number 8. The atomic number refers to the number of protons. That identifies the element. The atomic mass is the sum of protons and neutrons, just to reiterate and clarify. So O16 has 8 protons, 8 neutrons. O18 has 8 protons, 10 neutrons. Okay, so that's all very nice and handy. How does this help us reconstruct past climates? Let me start with oxygen, because this is the one that's widely used. Let's say I have a situation where it is in between ice ages. So we have sea level at a certain level, we might have some mountain glaciers, okay, no ice sheets on the land. So what happens? There is evaporation that takes place from the ocean. Water evaporates into the air and so on. Well, as we start to cool down the air temperature, okay, the rate of evaporation will start to cool down because cooler air holds less moisture. So whatever molecules of water that are able to evaporate, go into the vapor state, whatever those are, what we typically find is that the water molecules that contain the lighter oxygen, O16, are more readily able to go up into the atmosphere, especially when it gets cooler. So we have, okay, this moisture in the atmosphere, we have the precipitation, we get the snowfall, the snow accumulates over time, it compacts into ice, very nice and handy. Then we may have, so you have this ice core. Okay, then you may have a period where some of that melts, and then the water goes back into the ocean, sea levels rise, sea levels drop, and so on and so forth. The point of this is that if we were to take an ice core and we were to measure the fractionation, in other words, we measure the ratio of O18 to O16 as found in the ice cores, in the water molecule. How do we measure these ratios? We use a machine called a mass spectrometer. A mass spectrometer will actually measure the atomic masses. Very important analytical machinery. In essence, the short of it is, during an ice age, the ratio of O18 to O16 decreases. During periods in between ice ages, it increases because more of that water is able to evaporate into the air, containing more of the heavier oxygen because of the warmer temperatures. So let me repeat that again. During periods of glaciation, the ratio of O18 to O16 is less than periods of non-glaciation, where the O18-O16 ratio is increased. So using that, we can say, oh, the ratio is low here, the ratio is high here, ice age, non-ice age. And we see it. We can juxtapose that information by looking at tiny little organisms called radiolarians, foraminifera, and diatoms. And just to give you a flavor of some of the organisms. And what these are microscopic organisms, planktonic. What do they all have in common? They all have tests. Tests are basically shells that the organism lives in. What are the tests made of? Well, it depends on the organism. Diatoms, the tests are made of silicate. Silicate is basically a combination of silicon and oxygen. Forams, radiolarians, they might be made up of calcium carbonate, CaCO3. There's your oxygen, and there's your carbon in there as well. So let's consider the oxygen, to juxtapose what I just described with the oxygen levels found in ice cores. And we see a reverse. If there is less O18 that evaporates into the air to be deposited as snow becoming ice during ice ages, that means there is more O18 left behind in the ocean, which means the organisms are more likely to incorporate more O18 when they make their shells, their tests. Conversely, when more O18 is able to evaporate into the air during non-glacial periods, there's less O18 in the water for the organisms to incorporate. That's true whether it's in silicates or in carbonates. So, what do we see? We see a higher O18-O16 ratio in the organisms during ice ages and lower during non-ice ages. So, ice cores from the glaciers shows low O18-O16 ratios, but when we examine the organisms and we do a sediment core and we pull up, we call them ooze, a very scientific term, but we call them ooze. When you look at the ooze and you look at the organisms there and we measure those isotopic ratios, that fractionation, low O18-O16 ratio in the ice, high O18-O16 ratio in the shells. That is what happens during an ice age. Non-ice age, O18-O16 ratio increases, it decreases in the shell. It goes like this. And we can juxtapose that, use it as verification and validity of our techniques. So we can test that. You take a core and you run the samples. You run the isotopic fractionation and you look at the ratios. And then you can, using this information, you can then reconstruct past climates. It is also able, have the ability to use the carbon isotope to reconstruct global temperatures. Again, looking at the oxygen. We can look at in addition to looking at the oxygen fractionation in the shells to ascertain climate, whether it's ice age or not, we can use the oxygen in conjunction with the carbon to determine what the temperature was. So it should not come as a surprise to you, if we extend this further, a logical line of thinking, that if there is more O18 left in the water during ice ages, then guess what? We would expect to have cooler temperatures when the O18-O16 fractionation is higher in the organisms and lower in the ice cores, and vice versa. There's also something that physiologically changes with the organisms when they incorporate the carbon aspect for those who make carbonates. Somehow, during ice ages, the fractionation of C13 to C12 is higher. So we will see a higher fractionation of C13 to C12 in the organism during ice ages, which is also telling us what? That the temperatures are cooler. So I'm just giving you a very brief general overview, but I'm hoping that this gives you a handle or at least an idea of what is happening with the fractionation and how scientists, climatologists, can do these analyses and then reconstruct past climates. So when you see the charts, when you see the graphs of the fractionation and then looking at the temperature and so on, this is how it's done in essence. There are other techniques. You can use dendrology, which is taking cores from trees, and again you look at the ratios of nitrogen and carbon in there and look at the information that tells you. Botany is not my specialty, so I am not as up on that as botanists would be, but that they also use that to ascertain past climates. So it's another tool, another method, another technique to help reconstruct past climates. And it has been demonstrated very clearly, the data is quite clear on this, that increase the levels of CO2, temperatures go up. Decrease the levels of CO2, temperatures go down. And by using what I just described to you, we can reconstruct, and we basically say, oh yeah, temperatures were low here, and look what? We have an ice age. Temperatures were higher here, and it was not an ice age. And we track that. And again, it comes back to the point I keep making in these videos. It's the rate of change. It's much, much faster during the last almost 200 years, basically from the start of the Industrial Revolution, than it's ever been that we see in the record before. Professor Michael Mann at University of Pennsylvania made the famous so-called hockey stick graph, where we see levels of CO2 and temperatures kind of tracking nicely, and they both kind of go whoop, like that, though he had reached the heel of the stick, and the rate shot up. And we can trace that back to the start of the Industrial Revolution. So, as I said, I wanted to just to kind of give you an idea of what's meant by isotopic fractionation, what the general concept of it is, and in general terms how it's used. So that when you see papers or you hear scientists talking about it, you kind of go, ah, I understand what they're getting at. Hope you found this video informative, even if it's on a kind of a basic level. But I didn't want to get too technical, because then it can get crazy. But just want to give you a general idea of it. Please share, please subscribe, and I hope you'll become a patron. Thank you for your time.